Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so this session we are going to analyze BIM using moment distribution method. So we will consider support settlement, and we will calculate the member and moment in BIM, and after that we will continue to draw shear force diagram and bending moment diagram. So this is series number 1. Okay, so let's look at the screen right now. So we have here a continuous beam ABCD. So AB is subjected by point load at the center. There is an applied moment clockwise 120 kilonewton subjected at B, and for member CD we have 15 kilonewton per meter UDL along member CD, 5 meter length. Okay, so in moment distribution method we will determine the member and moment number 1. Okay, and after that we will calculate the vertical forces for each joint and then draw shear force diagram first, and the bending moment diagram we will draw based on the shear force diagram. Okay, the shear force diagram in order to determine the salient point in the bending moment diagram. The moment that we get from the table is actually the bending moment, the moment in the diagram, in the bending moment diagram, but the salient point, whether it has maximum moment or not, will be determined from the shear force diagram. Okay, so we have to start with the first step. So the first step we have to calculate K and distribution factor. Okay, so since I mentioned just now, we are considering the support settlement. So let's say we have support settlement at C. Okay, let's say we have support settlement at C. Delta at C is equal to 0.003 meter. Okay, 0.003 meter. Okay, now we are going to analyze the member and moment due to external loading first, and after that we have the second part of analysis. We calculate member and moment due to support settlement. Okay, anyway we will use the same distribution factor for both part. Okay, so we start with K first. K for AB, we have three members. We have K for AB. Okay, K for AB is, we assume that EI constant. In this case, EI constant. EI is constant. So KAB, we use 4 EI over L because far N here is fixed. This is far N. At A is far N, D is far N. So internal also considered as fixed. So we use all 4 EI over L for all members. So we calculate based on 4 EI over 4. So this is for AB. And then we have KBC for member BC. So for member BC, we have 1.5 length. 1.5 length. So we still use 4 EI divided by L. L is 1.5 here. And then we have CD 5 meter length. So we also use K equal to 4 EI over L. Okay, it is 4 divided by 5. 4 divided by 5. So we use this stiffness factor to calculate distribution factor. Distribution factor for A and D. A is fixed, D also fixed. For fixed and distribution factor is equivalent to 0. Distribution factor equivalent to 0. So DF for AB, which is equal to DF for DC, and this is equal to 0 because of the fixed end. So this is due to fixed. fixed n. Okay, and then we have to calculate. We have to calculate distribution factor for another remaining four n. Okay, using formula df is equal to, formula to calculate df is equal to k divided by total k. K divided by total k. K divided by total k. And after that, we will move to part A. So we move to part A. So part A, we will calculate FEM due to external loading only. External loading only. Part A. And part B, we will calculate based on support settlement only. Support settlement only. Okay. Part A, we will calculate using external loading only, means that we have to calculate fixed end moment due to external loading only. Formula is given in appendix normally during examination. And part B, we will consider only support settlement. Okay, so we will move to Excel. Okay, we move to Excel. So we want to calculate K. So back to this, K is 4 EI over 4. KAB is 4 EI over 4. So I will put here 4 divided by 4 is equivalent to 1. Okay, 1. So same goes to here. AB and BA is the same member. Okay, we should get the same value for AB and BA, it representing member AB. Okay, for BC, we have 4 divided by 1.5. 4 divided by 1.5. Okay, it is 4 divided by 1.5. So we get 2.667. So will be equal. And for CD, we have 4 divided by 5. 4 divided by 5, it is 4 divided by 5. EI is constant, so we get just like this. Okay, so here is how we calculate the stiffness factor. Of course, you have to do it manually. Okay, now we will move to distribution factor. Distribution factor for BA means that BA is 1 divided by total. Total means BA plus BC. Member stiffness divided by joint stiffness. DF is K divided by total K. Total K means joint stiffness. So means that we have to divide by total BA plus BC. Total BA plus BC, it is 1 plus 2.667. 1 plus 2.667. It is 3.667. 1 divided by 3.667. So we get 0.273. 0.273. And for BC, distribution factor for BC, it is actually 2.667 divided by 3.667. Okay, it is BC, KBC divided by total K. KBC divided by total K, or it is equivalent to 1 minus 0.2. 1 minus 0.2. Okay, here it is 1 minus 0.273, we get 0.727. And distribution factor for joint means that BA plus BC means that it is joint B, so total distribution factor for joint B must equivalent to 1. Okay, so we do the same for member for CB and CD. Okay, CB and CD. So for CB means we have to take KCB. We divide by total K. Total K at joint C. It is CB and CD. So it is 2.667 plus 0.8. Okay, so we get 0.767 0.769, and we get another value, okay, by using 1 minus 0.769, it is equivalent to 0. It is equivalent to 0. Okay, now we move to the fixed end moment. Okay, fixed end moment. So we have here for member AB, fixed end moment for AB. So this is 160. So this is 160. Okay, 160. So we have AB here. This is A, this is B. Okay, and moment acting in this direction. So means that one negative, one positive. Okay, this is 2 meter, 2 meter. Okay, so for point load, we use PL over 8. For point load, we use PL over 8. So this is PL over 8. This is also PL over 8. Refer appendix. Okay, PL over 8. PL over 8. PL over 8. So we transfer this formula to Excel. It is PL over 8. For AB, FEM AB, it is negative because of the behavior. P is 160. L is 4 divided by L is 4 divided by 8. Okay, we get negative 80, negative 80. So BA, we should get positive 80. Because due to loading, we will get one negative, one positive. Negative, positive. Okay, negative, positive. This is 80. Okay, BC doesn't have external loading. We have UDL. We have UDL we have UDL for member CD. So for UDL, we use formula to calculate the fixed end moment for UDL. It is like this, UDL. So this is 15 and 5. This is 15 and 5. So we will have this behavior for the fixed end moment. So the formula is WL squared over 12. WL squared over 12. WL squared over 12. W is 15. Length is 5 meter. Okay, it is W 15. Length is 5 times 5. WL squared over 12. Okay, one negative, one positive. One positive. Okay, and careful because in this question we have joint moment. In this question we have joint moment. Remember, the moment that we distribute is joint moment. The moment that we distribute is joint moment, means that at distribution, for the first distribution, we have to consider this 120. This 120 joint moment. So this one is joint moment, means that we don't have to change sign. The member end moment, the fixed end moment that we calculated just now, when we distribute, we have to change sign, but we don't need to do that for joint moment 120. Okay, so I put 120 at B, at joint B. So I add another row to include the joint moment. So it is located at B, it is 120. At B, it is 120. So this is 120. And it is positive. It is positive. This is 120. Okay. This is 120. This is 120. FEM. Okay. So now we want to total the joint moment. We have applied moment 120 here. We have 120. And we have FEM at B, which is 80. And remember, this 80, we have to change sign because it is opposite with joint moment. So what we should get is for the first, for the joint moment, the total joint moment. So we get here negative 80. Negative 80 plus 120. Negative 80 plus 120 means that the moment that we need to distribute is now equal to 40 only. 40. Okay, because we have to plus with 80, but the one that we have to consider is not 80 but negative 80 because of fixed end moment opposite with joint moment. So it is negative 80 plus 120, so we get 40 here. 40. And for CD we get positive 31.25. 31.25. 31.25. So I clear this one first. Okay, look at the process. Okay, for the distribution, it is joint moment times distribution factor. Joint moment times distribution factor. So it is joint moment time distribution factor 0.273. Joint moment times distribution factor 0.273, so we get 10.909. Okay, again, joint moment 40, we have to times with 0.727, so we get 29.091. 29.091. Okay, so move to joint C, so we have 31.25. So this is already joint moment. This is already joint moment, so it is joint moment times with factor. Joint moment times with factor 0.769. 0.769, so we get 24.038. And joint moment times factor, we get 0. The factor is 0.231, so we get 7.212. Okay, then step after distribution is carry over. The step after distribution is carry over. So we need to carry, we have to cross boundary. So let's look at the boundary. We have boundary here. We have the boundary like this, the boundary. So we have to cross boundary. So that is why you can see that I have put the color to representing the process. Okay, to represent the process. So we have 10.909, we have to carry to A. So it is 10.909 divided by 2. This is 10 divided by 2. So we get 55455. Okay, so 29 BC, we have to carry to C. We have to carry to C. So it is 29 divided by 2. Okay, and 24 at CB, we have to carry to B. So divide by 2 because the factor is 0.5. The factor is 0.5. A and B both are fixed, so we have the same factor. Okay, 7.212, we divide by 2 as well. Okay, we divide by 2 as well. Okay, next we move to the second distribution. The second distribution, so okay, let's check whether it use the same, the right column. Okay, I clear this one first. Okay, so this is distribution. This is distribution. So we have to repeat the process. Distribution carry over, distribution carry over. So for the second distribution, this is the second distribution. The second distribution, again, we have to find the joint moment. This one, we don't need to put another row for joint moment. Okay, we put previously one row for joint moment because we have to plus with the applied moment that is subjected at B. Okay, then we just need to continue. Okay, so I put negative to represent joint moment here. So total is 0 BA plus BC. BC is 12. So we have to time with the factor. The factor is 0.273. The factor. Okay, so we get 3.278 negative. Okay, we should get negative because the joint moment is opposite with 12.019, this one. Okay, so it is BA plus BC. BA plus BC, we have to time with the factor 0.727 for BC. Okay, 0.727 for BC. So we get 8.741. So this four value, okay, this four value 12.019, negative 3.278, negative 8.741, total must equal 0. Okay, so we repeat the process again for joint C. So for joint C, I put negative to represent the joint moment opposite condition. Okay, it is 14.5 plus 0. 0 for CD. So this one plus 0 times with factor is 0.769. 0.769. Okay, look at the process. You have to do it manually. So 14 plus times factor 0.231. 0.231. Okay, so for the second distribution, so these two value, okay, 14.545, negative 11.189, negative 3.357. Okay, you have to total this and check whether you get 0 or not. Okay, because total moment equivalent to 0. Okay, so carry over, we repeat again the carry over distribution. So okay, I copy the formula for distribution. Okay, just to double check whether this one is correct or not. Distribution 0.064 negative, so get the same. 0.03. Okay, so this is right. Okay, now once we have find the 0.0 something in the last distribution, means that we have to stop. We need to stop the process, and we have to find the total moment. The total moment start from, okay, this one I delete first. Okay, we have to find the total moment. Start from fixed end moment, and then distribution until the first distribution until the last distribution. Okay, so I just need to find all this using formula. So sum all this until the last distribution, but don't forget we have to plus with the fixed end moment. Plus with fixed end moment. Okay, so negative 75.576. Okay, this one is 88.878 for BA. For BC, we get 31.122. Total is 120 because we must get back the moment 120 that we apply at B. Okay, that's why we don't get 0 here, because at B, MB is equal to 120. Okay, so we get CB 26.761. CD, it should be negative. Okay, because this one moment equivalent to 0. CB plus CD, the moment equivalent to 0, and BA plus BC, the moment is equivalent to 120, because in the question 120 is given as an applied moment. Okay, and DC. Okay, so this is the value that we get. Okay, if you do it manually, make sure you get this answer as well. Okay, now this is the end moment, the member end moment, considering external loading only. Considering external loading only. So this is part A. Okay, so this is part A. This is part A. So we get moment like this. Okay, now we want to move to part B. Part B where we have support settlement. Support settlement as I have chosen here. Okay, it is occurred at point C, okay, of magnitude 0.003 or 3 mm. So let's see how we analyze the support settlement. The first thing to do, you have to draw the free body diagram because we want to find the behavior of the behavior after support settlement is considered. Okay, we have to draw this free body diagram first. Okay, now we want to do part B, part B. So this is part B. This is support settlement. Okay, delta at C is equal to 0.005. 0.005 means that we have like this. Okay, we label as A, B, C, and D. Okay, C is settled. Means we have to draw the settlement at C. A, B remain at same position. B, we have to join with the new C position. The new C position is like this. Okay, means that this will be the C, the new C, we call it as C prime. Okay, and this is the new position after support settlement. Okay. Okay, this is the delta at C, and this is equivalent to 0.003 meter. Okay, 0.003 meter. Okay, so look at the behavior after settlement occur. AB remain the same. BC, okay, we consider member BC first. Consider member BC. Okay, member BC after after support settlement become like this. Okay, new position of beam BC after settlement. Okay, so now we have to identify the behavior. The behavior means that the moment will push back both end B and C to its original position. And always remember, original position for beam is horizontal. So we have to draw the horizontal line at both B and both end. Okay, so this is the horizontal position, and then the angle will be measured from original position. From original position, we measure the angle. So it is positive angle. This is called as Scott rotation. Okay, this is called as Scott rotation. And between this angle and FEM, it is opposite because we have to apply moment. To push back the beam to its original position. Means that we have to apply moment in this direction. So that we will get back to original position. So between angle and FEM, it must be opposite. Why we need to do this? Because the angle will be determined easily because we measure from its original position. Okay, and angle and FEM, the condition is opposite. So we can conclude that angle positive angle positive, FEM will be negative. FEM will be negative. Then we have to apply formula. We have to apply formula. The formula to calculate FEM, due to delta, FEM due to delta. So we will calculate A and B now. A and B. Sorry, this is not AB, BC. This is BC, right? BC, B and C. So we get FEM-BC, which is equal to FEM-CB. Both have same behavior, same sign. Okay, so we get, so because we must get negative, so we put negative in the formula. Okay, because the FEM must be negative, so we put negative. So we calculate using formula. So it is 6 negative 6EI 6EI delta over L squared. This is the formula. 6EI delta over L squared. 6EI delta over L squared. EI normally 200 and 500. Okay, delta is 0.003. L for member BC is 1. L, what is the L value? L is 1.5. 1.5. So we use this formula. We use this formula to calculate FEM for member BC, and it is negative. It is negative FEM because the angle is positive. The angle is positive. So when we move to CD, CD is like this. This is CD. Okay, this is CD. So we have to draw the reference line. The reference line is always horizontal. This is the reference line. The reference line. And we measure the angle from reference line. This is negative angle. Negative angle. Negative angle. Negative angle means chord rotation is negative. Means that FEM will be positive. FEM will be positive. FEM positive because we apply moment like this. FEM is positive. So that when we apply positive FEM, we will actually the moment will push back the beam to its original position. So when we want to calculate this, when we want to calculate for member CD, this is for CD, this is for C and D. So FEM for CD equal to FEM for DC, and this is equal to positive 6 EI delta is 0.003 divided by L for CD. This is L squared. Okay, divided by L squared. Okay, so we use this formula in Excel again. So we have negative 6 EI delta over L BC 1.5, and we have 6 EI delta positive 6 EI delta over L squared. L is 5 meter for member CD. Okay, I open back Excel. Okay, open back Excel. So we have to use the same distribution factor, the same stiffness factor. Okay, so the difference is only due to FEM. So FEM, we have to calculate FEM for BC and CB. FEM for BC and CB. Okay, for member BC, refer back to this member BC. So FEM is negative. So we put negative 6 times E is 200. 200, I is 500 times 0.003. 0.003 divided by 1.5 square. So we get we get negative 800. We get negative 800, and it is equal for CB. BCCB has same value. Okay, and then for CD, we should get positive FEM, positive FEM, because the angle is negative, FEM is positive, so we apply positive. Okay, to calculate FEM for CD, the behavior shows positive. Okay, so it is 6 times E times 500 times 0.003 divided by length is 5. Now length is 25. So we get 72. Okay, we get 72. Okay, we double check. It is 6 times 200 times 500 times 0.003 divided by 5 squared, 25. Yes, 72. Okay, previously we have 6 times 200 times 500 times 0.003 divided by 1.5 square. 1.5 square, so we get 800. Okay, that is correct. So this is also 72. 72. Okay, so just checking this back. Okay, for distribution, total moment I put negative, so you have to also to put negative. Okay, this is 0 BA plus BC plus BC, 0 plus BC times with factor is 0.273. Okay, we get 218.182, 218.182 BA plus BC times 0.727, 0.727. Okay, 581.818 total this. Okay, total this must equal 0. Okay, and then we move to joint C. So joint C we have negative 872. Okay, plus not plus, times with 0.769, the factor 560. Okay, total moment CB plus CD times with factor is 0.231. Okay, so we have to check negative 872, negative 872, 560, and 118. Is it the right one, the right answer? Please check back. Okay, double check. So what we get this? $800 CB plus 72 times with factor 0.231, 168. Okay, this one is correct. Okay, it is negative 800 plus 72 plus 560 plus 168. We get 0. Okay, so check back. We have to make sure that total must equal 0. Okay, so then we have to carry over. Okay, we have to cross boundary like this, like this. Okay, cross boundary. Okay, cross boundary. So we should get, okay, 109.091, and then we get 280 from 560. 280 we get from 560, and then we get 290.909 from 581.818. Okay, and then we get 84 from 168. Okay, so repeat the process: distribution, carry over, distribution, carry over. And okay, I just need to check back. Negative 76, is it correct one? Yes. 30.515. Negative 10. 4.268. 1.9. 1.4. And 0.57. Okay, so then we can continue again, because we don't get 0.0 yet. Okay, copy, carry over. Okay, distribution. We get 0.2, 0.5. Okay, carry over again. Carry over. This is carry over. Distribution. Carry over. Distribution. 0. Maybe another 1 cycle. Okay, carry over. Distribution. Okay, 0.1, then stop lah. Okay, carry over, distribution. Okay, so the answer, total from, okay, total start from the first fixed end moment, the first moment in the table. It is fixed end moment. Total start from fixed end moment until the last distribution. Okay, 82.449 for AB. BA, we get 164.898. And then for BABC, negative 164, total must be equivalent to 0. Okay, because this one we don't consider the joint moment. This is due to support settlement. Okay, 189.176, so we should get positive. Okay, we should get positive. 198 doesn't matter. 130. 130. Okay. $78, $31, $11, -4, $2, -1, 0.214, 4. Okay. 0.460. Okay, this 0.064. Okay. So seems good. So we get like this. 560. 168. Okay. Okay, this one we get 1981, 189, 189, 189.2, 189.2 doesn't matter, so we can consider as 189. Okay, 130, 130.6, 130.6, this one 82.449, this is 164.8, 164.8. Okay, plus minus 0.1 doesn't matter. Okay, so this is the member and moment due to settlement. Member and moment due to settlement. I copy this. So this is due to settlement only. Okay, due to settlement only. Okay, so now we have two table. Part A, due to external loading only. We have to consider also the joint moment 120 at point B. And then we have table number 2 for part B. This is considering support settlement only. So we get the new end moment. So the total means we have to total, okay, this part A and part B. So the end moment should be okay. So now we have to total the moment. So we want to find the moment, member and moment. Member and moment. Okay. So it is M total. So this is MA plus MB. Okay. MA plus MB. So MAB we get negative 75, negative 75, 75576, negative 75576 plus with 82.4, we have to plus with 82.449. Okay, total these two. Negative 75, negative 75.576 plus with 82.449. So we get 6.873 kilonewton meter. Okay, so we calculate for MBA. So MBA, this one is 164.898. 164.9. So it is 88787. 878. 878. 88 point. This is 88.878. Okay, we get 164.9. We get 253.778 kilonewton meter. Okay, so for BC, for BC we have 31.122. 31.122. Okay, for MBC it is 31.122 plus with negative 164.8 plus with negative 164.8.9. Okay, so we get 31.122 minus 164.9. So we get negative 133.778 kilonewton. Okay, so MCB. Now MCB is ABBA, BC, CB, 26.761. 26.761 is 26.761 plus with 189, 189.2. So negative. It is negative 189.2. Negative 189.2 equal to 26.761 minus 189.2. So we get negative 162.439. And then we have MCD and MDC. MCD negative to 6.761. Negative to 6.761. Okay, we have 189.288 because we assume 0.2. So this is 189.2. So we will get the same. We will get the same. Positive 162.439 kilonewton. And last value is 33.485. 33.485. This one is 33.485. Okay, and 130. We have to plus with 130,644. 130,644. 130,644. 130,644. Okay, we get 164.129. Okay, so we have 6 member and moment, MAB, MBA. So let's sketch the moment sign, moment direction. Okay, the moment. So MAB is positive, MBA is also positive. Positive, so the moment positive. So it is positive and positive. Both are positive. Okay, MBC, MCB. MBC, MCB, we have negative. We have negative, and negative. Okay, MCD, MDC, we have positive. Okay, so actually to see clearly, we draw like this. Okay, so what we get is, okay, wait for a while. Okay, now we want to move to the next section. We want to calculate reaction. Reaction means vertical reaction because moment has already determined from the table. So we want to complete with the vertical forces at support. And after that, we will draw the shear force diagram before we draw the bending moment diagram. So where is it? Okay, this one. Okay. Okay, it is positive, positive for AB. Positive, positive. Negative, negative, and positive, 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 positive. This is also positive. Okay, so means that we have to calculate. We have to calculate. So this is one. Is it 120? It is 160. 160, 2 and 2. So this is 160. So 160. We have, this is 2 and 2. So we have the vertical force. So this is called as AY. This is BY1. AY and BY1. Okay, the moment is 6873. This one is 6873 and 253778. 253778. And then we have, this is BY2, this is CY1. Okay, and then we have CY2 and DY. CY2 and DY. This one we have UDL. It is 15 along 5 meter length. This is 1.2 meter. Okay. Okay, now moment. This is 162.439 and 164.129, and we have 162.439 and 133.778. Okay, so we will analyze these three beam AB, beam BC, and beam CD, just like we analyze simply supported B. By taking moment at one end, we will get one vertical reaction, and then we apply total Fy, we will determine another one. Okay, so we consider AB first. Okay, we consider AB first. So member AB. So for member AB, we apply moment at A equal to 0. So focus on this one. This is AB. Okay, AB. So it is 6.873 plus 253.778. We have to plus with 160 times 2 minus 4BY1 equal to 0. So BY1 equal to, it is 6.873 plus 253.778 plus 160 times 2, 320, plus, okay, we divide by 4. So we get BY1 equal to 145.163 kilonewton. Okay, then we apply total Fy is equal to 0. So we can get AY value. So it is AY plus BY1 minus 160 equivalent to 0. So AY equivalent to 160 minus 145, 163. So we get 14. We get 14.837 kilonewton. So we get here the vertical reaction. Okay, the vertical reaction for member AB. Okay, the internal, the shear value, the shear value. So this is for member AB. And then we will calculate, we will continue to calculate for member BC and member CD. Okay, for member BC, so again, we have to take moment, this time at B. Total moment at B, which is equal to 0. Okay, it is 133.778 negative. 133 negative 133.778 minus 162,439. 162,439. Okay, we minus also, minus 1.2 CY. 1.2 minus 1.2 CY1. This is equal to 0. So we get negative, should be negative. So it is 133.778 and 162.439. We divide by 1.2. Okay, we get 246. So CY1 equal to negative 246.848 kilonewton. Okay, apply Fy is equal to 0. So we get CY1 and BY2. So BY2 equal to positive 246.848 kilonewton. Okay, so that is for member BC. For member BC, now we move to member CD. So for member CD, again, we have to take moment. So now at C is equal to 0. It's equal to 0. Okay, so we have here positive 162.439, 164.129. Okay, it is 162.439 plus 164.129 plus UDL is 15 and 5. 15 and 5. 15, 5, 2.5 minus dy, 5 dy. 5 dy. So it is 15 times 5 times 2.5 divided by 5. So dy equal to 102.814 kilonewton, and taking total force in y direction equal to 0. So we get okay. So we get CY2 plus dy minus 15 times 5. Okay, so it is CY plus 102.814 minus 15.5. So CY2 is equal to it is negative 27.814 kilonewton. Negative 27.814 kilonewton. Okay, we have to continue to draw the shear force diagram after this. Okay. Okay, that's the step. That's the step after we have finished calculating member and moment from the table. So for support settlement, of course we have choices. For beam with support settlement. Okay, of course we have choice to do separately or to do combining FEM. But because of the moment, the applied moment, so it's good if we do it separately. So we do part A considering external loading only. So we have to include the joint moment, the applied moment subjected at joint for the first part. And when we do part number 2, we consider support settlement only. So then we plus these two moment, and then once we get all the total member and moment considering both, and then we can continue to calculate R, to calculate reaction, vertical reaction actually, because we have already have the moment from the table. So we have to complete the vertical reaction because we want to draw the shear force diagram. Why we need to do this? Because we can identify the maximum moment in the bending moment diagram from shear force diagram. If not, we can only get the moment at the first point and the last point. But when we have shear force diagram, we can draw uh, the diagram with all the salient point. Okay, so back to the question, back to the solution. So this is support settlement considering delta at C equivalent to 0.003 or 3 mm, and in addition to that, we have joint moment 120 clockwise at point B. Okay, at point B, so I have divided into two parts. Part A, considering external loading only here. I add another row for joint moment. Okay, for joint moment. So please make sure that you know the process, because the moment that we distribute is joint moment. So that is why for the first distribution, I actually refers to joint moment, so we don't need to change sign because I already put joint moment here. Okay, we change sign because the member and moment opposite with joint moment, and we distribute joint moment. Okay, so repeat the process again and again until the moment reaches 0.0 something. Okay, we may stop at last distribution. Do not stop at carryover. You must stop at distribution and then total all the moment. For this case, special for this case, we have to plus all, start from distribution until the last distribution, plus the fixed end moment. This one plus all this. Okay, plus, and then you get joint moment. And to check whether we get the correct one or not, we can check MB total 88.878 and 31.122. We should get the moment back, 120 moment given in the question, applied moment. Okay, and then we do part number 2, part B, support settlement. In support settlement analysis, we have to sketch the diagram. Okay, because the diagram is very important, because we identify negative or positive from the behavior. Okay, even though in the question we mentioned the delta, the support B settle by 3 mm downward. So downward doesn't mean negative or positive. So we get the behavior we get the sign from behavior. So we need to draw the diagram first in order to identify the behavior. Okay, so just don't do like this. So draw one line representing beam, and draw where is the settlement occur. It is occur at C. So C, we have new C position, C prime. So we have to join B, remain at same position. D, remain at same position. Okay, remain at same position, remain at same position. So we have to join B to C prime and C prime to D. So we get these two triangular, So from this triangular, then we identify the behavior, whether it is negative or positive FEM due to support settlement. So we consider member BC first. Member BC first, draw the line, draw the beam line after settlement. Okay, and identify the chord rotation or the angle, and the angle will be measured from original position, and original for beam is horizontal. So why we need to do this? Because it is much easier to check the sign for FEM by doing this step. Okay, so identify the angle. Angle will be measured from original position, which is horizontal, to new position, and then the FEM is opposite. Okay, so angle is positive, angle is positive, angle is positive, FEM is negative. Angle is positive, FEM is negative. So we have to apply negative in the formula. Okay, do not compare with frame analysis, because the side sway have different behavior. Okay, so FEM, we should put negative in the formula, because we should get the negative behavior. Okay, and same goes to member CD. We should get positive FEM, because the angle is negative. Okay, so we put positive in the formula. We put positive in the formula. So we calculate based on this formula. Okay, and then we get the new FEM. For BC, CB have the same sign, CD, DC have the same sign. Okay, so we have to repeat the process in the table. Distribution, carry over, one cycle, repeat again, distribution, carry over, distribution, carry over. Careful with the far end condition, because the carry over factor will be depending on the far end condition. So in this case, we use all 0.5 factor. So finally, we get end moment for part B, means end moment due to support settlement. So since when settlement occur, external loading is still there. So we have to plus these two. We cannot give the answer just due to support settlement only. Cannot. When support settlement occur, we have to plus the moment. Because when settlement occur, the loading is there. So we have to plus. So that is why I explain this step. So member and moment, M total, we have to consider part A and part B. So we plus it directly. We don't have correction factor like what we have done in frame analysis, frame with side sway, because in frame analysis it's different. The delta is unknown. In this case, the delta is given, 0.03 is the delta. So we have FEM due to support settlement. We have FEM due to delta, so we can plus directly without having the correction factor. Okay, so we due to the moment sign, we can sketch the position of the bending moment diagram, the position actually, and then due to this also we can determine the vertical reaction. So we normally determine element by element or member by member separately. Okay, this free body diagram actually you can find in the chapter number 11 textbook under slope deflection method. Okay, so we actually analyzing just like simply supported beam. We apply moment, we apply equilibrium equation, apply moment, and then we apply total we apply total force in y direction because it is beam. Okay, x total fx is ignore because there's no horizontal force, horizontal reaction, horizontal displacement. Okay, so we do one by one. Member AB, we determine BY1 and AY. For member BC, we determine CY1 and BY2. For member CD, we determine DY and CY2. Okay, so this is all the shear value at each end, shear value. Okay, so now we want to draw the diagram. We want to draw the diagram. We will start with shear force diagram. Okay, if after we draw the diagram, we don't close the diagram, because the diagram must always close, start from zero, end at zero, because start at zero, end at zero means the system is in equilibrium. If we don't get zero, means we have to recheck the answer, whether we have missed something, so we don't get zero. Okay, so we start with draw. Okay, draw it separately so that we can see it clearly. So this is A, B, B, C, C, D. Okay, this is shear force diagram. Okay, shear force diagram. So we have point load. This is 160. We have UDL. We have UDL. We have UDL 15, 5. Okay, before we draw the diagram, the shear force diagram, okay, we draw the free body diagram first. Okay, so AY 14,837, 14,837 and 145,163. 145,163. Okay, moment, positive, 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 moment, positive, positive. For 6873, 6873 and 253.778. So this is 6.873 and 253.778. Okay, and then for BCCB, we have 246.8. 24. Okay, it is 246.848. 246. 246.848. 246.848 positive, negative. Moment is negative 133.778 and 162.439. Moment is negative, negative. Moment negative, negative. Moment is negative. Negative. 133.778 and 162.739. 739. And then we have CY2. CY2 negative 27.814 and positive 102. 102.814. Moment positive 162.4339 plus 164.129. Okay, positive, positive. This one is 162.439 or 739. 439. 439. This is 439. 439. 439 and 164.129. 164.129. Okay. Okay, then we can draw the shear force diagram. We can draw the shear force diagram. Where is the ruler? Okay, close first. Okay, now we want to draw the shear force diagram and see whether we get the equilibrium for all value that we have just calculated. Okay. Point load. Okay, this is B. Okay, this one is just the dotted line. Just like the dotted line where we can use to draw the shear force diagram and the moment diagram line. Okay, so okay, now we draw the line for shear force diagram. Okay, we draw the line for shear force diagram, this one. Okay, AB, BC, CD. Okay, like this. Okay, so 14.837 means going up 14 by 14.837, going up by 14.3837 here, and then minus 160, go straight again, and close at 0. This is shear force diagram. We draw by using all the shear value. Okay, so this is 14.837 and 145.163. This is positive, negative, 2 meter. This one is 2 meter. This is also 2 meter. Okay, this is shear force diagram for member AB. Okay, now we move to BC first. So we have 0 and positive 246. So we have to draw going up like this, straight, down, okay, so this is positive. The value is 246.848. The length is 1.5 meter. Okay, kilonewton. This is kilonewton. This is kilonewton. Okay, and then for CD, it is now negative 27. Negative means we draw down. Okay, negative 27, and then 15 times 5 also negative. So we get this. point and this. So we don't get intersection. Intersection means we don't have maximum moment in the bending moment diagram for member CD. Intersection, we get intersection for AB, but we don't get intersection for CD. Okay, this is 27.814 kilonewton. This is negative. And we minus by 15 times 5, we get in total 102.814 negative. So we plus back with 102, we plus back with this, we get back to 0. Okay, so total length is 5. So this is trapezium. So once you get trapezium, means there is no maximum moment in CD. So this is 5 meter. Okay, so this is the shear force diagram. This is the shear force diagram. The shear force diagram. So this is A, B, C, D. Okay, now we will check whether the based on the value, based on the shear force diagram, do we get the right moment, same with the moment in the table. Okay, the moment in the table. Okay, so I just need to continue this line. This is for the bending moment diagram. Okay. Okay, draw the line for the beam. Okay, we have AB, BC, CD. Okay, so we will start with the first moment. The first moment is 6.873. Okay, for the bending moment diagram in analysis, okay, you can choose either you want to set positive, okay, on top of the line, okay, or below the line. It's up to you. Okay, above the line or below the line, doesn't matter. But when you draw bending moment diagram for design purpose, you have to draw negative. Okay, negative up. Okay, above line negative, below line positive for the design purpose. For analysis, you can do both, doesn't matter. Okay, so I choose to put positive above line, negative below line, positive, negative. So means that when I need to draw the first moment where the moment is positive, so the value is somewhere here. Okay, somewhere here. Okay, so the moment is 6873. 6873. 6873. 6873, it is positive. Don't forget the first value is 0. The first value is 0 because as I mentioned, the diagram must be starting from 0 and close at 0 to represent the equilibrium. If you don't get 0, means something wrong somewhere, you have to check back. Okay, so start with 0. So 0 is the first position. Then the moment position, the first moment position is 6.873. And then we continue by using the area of shear force diagram. We have to time with the moment. Okay, so now the moment is 6.873. 6.873. We have to plus with the area. Okay, which area? this area. Okay, we have to plus. Plus because the label in the diagram is plus. Okay, so it is 6.873, 6.873 plus with 2 times 14.837. We got 36 positive. 36 positive means the point is somewhere here. Okay, so it is 36.547. And then we have to minus the second one. We have to minus the second one. This one. We have to minus 2 times 145.163. And the answer should be the same with the moment here, but in opposite sign. We cannot get same sign because we want to close loop. We have to plus these two. Okay, we get negative 253 and the moment in the diagram is positive, means it is correct. Okay, so we get negative 253. We get here. Okay, 253 253.779. 253.779. So we complete the diagram. Draw, start from 0 and then just join the dot, the cross dot. Okay, join and join. Join and close. Remember to close the diagram. Okay, to close the diagram. So we get this. This is the bending moment diagram. This is positive, this is negative. Okay, for member A, for member A and B. A and B. Okay, now the moment at at B, for member BC. So we get one negative, one positive. Sorry, both are negative. So we get one below line, one above line. I mean, okay, one below line, one above line. It is 133.778. 133.778. 133.778. Another one is above line. So for this one, we don't have to actually from the moment that we get from the table, we can get this directly. But if we want to check whether we get 0 or not, just we can check from the shear force diagram. Okay, 162439. 162439. 162439. Okay, negative and positive. Okay, so now we have trapezium. The moment is 162439. The moment is 162439, somewhere here. 162439. 162439. Okay, we have to minus the area of trapezium. We have to minus the area of trapezium. Okay, then we should get the last moment value 164.129. Okay. Okay, the area of trapezium. The area of trapezium we have 102,814. 102,814. The area of trapezium. Area of trapezium is 1/2 times 27.814 plus 102.814. Okay, 7.814 plus 102.814 times 5 divided by 2. So it is 326.57 area of trapezium. Okay, the area of trapezium. Area of trapezium is kilonewton meter. Okay, so the moment is 162.439. 162.439. We have to minus 326.57. Okay, so this value, this one, 162, it is positive because it is above line. Positive, it is above line, 162.439. We have to minus the area of trapezium. The area of trapezium is 326.57. We have to minus because in the shear force diagram, the sign is minus, is negative. The sign is negative. So it is 162. It is 162.439. We minus by 326.57. We get negative. We get negative 146. Negative below line. 164.131. Okay, this is negative because we will plus back with the last moment in the diagram, which is positive 164.13. 129, 13 doesn't matter, 13. So 164.13. So when this value we pass with positive in the diagram, means that we get back to 0. Remember the diagram must start at 0, end at 0. Okay, start at 0, end at 0. So how the diagram look like? 90. Okay, this is vertical. Okay, now we don't have maximum moment. So how the diagram look like? We just need, remember this is UDL. UDM means we have curve, we should get curve line. The detail line for this curve, actually we can get from the equation, because the bending moment diagram is actually we can calculate the accurate value when we substitute x value. Okay, doesn't matter. So just draw like this. Without maximum moment, we will get like this. Okay, again. Okay, wait. Without maximum moment, we get like this. Still under eraser. You just need to join these two dots lah. You just need to join these two dots. Curve line. Do the curve line, not straight line. It must curve. something like this. Okay, so this is positive, this is negative. So this is the end of analysis. This is the bending moment diagram. So this is bending moment diagram, and shear force diagram is here. Okay, so we identify whether the salient point or the maximum moment in the bending moment diagram from the shear force diagram. That's why the shear force diagram is important for you to understand. Even though we can draw the first and the last point at each end without having shear force diagram, but you need to actually in design you have to determine the maximum moment, and we get the maximum moment from the area of shear force diagram. So this knowledge is very, very important for you to understand. Okay, actually you can sketch directly the bending moment diagram, the first and the last point, but we get the maximum moment and we identify the right shape, okay, from the shear force diagram. For example, for member CD, we get trapezium. What does it mean? Uh, what does it mean? Means that we have no maximum moment for member CD, maximum moment, because there is no intersection. Okay, like what I have explained previously, there is example where we have maximum moment. The inclined line here uh, cross have intersection. Okay, this line have intersection, this line have intersection. Maybe the position is like this, have intersection. Means this intersection means the bending moment diagram has maximum moment. But in this case where we have trapezium, we don't get the maximum moment. So when we don't get the maximum moment, we the bending moment diagram we just draw like this. So this is for member C D. This is for member C B C. Okay. So this is the solution, the full solution of this beam. Okay, this beam. Of course, if we don't have applied moment, at B, it is easily if we just plus analyze in one table. We combine FEM due to external loading and support settlement earlier. But for joint moment, when we have applied moment, so it's good if we can do it separately. Okay, so before we end this session, so I go through again this one. So this is beam analysis. We have four nodes A, B, C, D. So there are 160 point load at the center of member AB, joint moment or applied moment at B. CD is subjected to UDL along CD. So in addition to that, we have support settlement at C of magnitude 0.003 meter. Okay, so calculate K and distribution factor first. Make sure you use the right formula for K. Please look at the far end condition at A and D. Okay, so after that, we just need to continue part A, part B. So part A, we just consider the external loading, and part B, we consider support settlement only. So in part A, due to external loading, so because of an applied moment at B 120, so I have actually add one extra row, two extra row actually, applied moment and joint moment. Okay, because we need to include this 120 when we distribute moment. Okay, when we distribute moment, that is why I add another two row in this table, applied moment 120. And applied moment is subjected directly at joint, so it is joint moment, but we have to plus the joint moment that we get from the fixed end moment. So that is why we get 40 here. So that is why we get 40 as joint moment. So when it is joint moment, we don't need to change sign. We don't need to change sign. That is why we get 40. This 40 we times with 0.273, we get 10. Positive also. Join moment. We distribute join moment. And after that, we do carry over. Then from carry over, we continue the next distribution. But so this time we don't need to put another row for join moment. So we just need to put negative to represent join moment. So we repeat the process. Okay, until we reach or we get 0.0 something, so we can stop, and then we have to plus all the moment. When we plus all the moment, you have to check back member join B. At join B moment total must be equivalent to 120 back. The means that we get back the join moment that is applied at B in the beginning. Okay, so then we move to part B. Part B, so we have to understand the support settlement. We have to draw, we have to sketch the diagram, because the diagram will guide us to analyze support settlement, fixed end moment due to support settlement, because the sign that we put representing behavior. So we consider each member one by one. AB does not get any effect, so remain the same. So consider member BC. BC we have negative FEM because the angle is positive. The angle is negative for CD, so we get positive FEM for CD. So we apply FEM due to support settlement in table number 2. So we repeat the process, and we get the new member and moment. This is MB. So we total all the moment. So after that, we have to complete this with the shear value. Not only moment, we get moment value from the table, and we have to complete the shear value by doing static equilibrium analysis. It is just like we analyze simply supported beam. Okay, we put all the information, we label all the shear AY, BY1, BY2. BY1, BY2 means when we plus these two, we get BY. CY1 means and CY2 we get CY. AY, BY we only have one AY, one BY, so that's why we get like that. Okay, so we analyze one by one, just like we analyze simply supported beam. So we will get all the shear value. So this shear value will be using in the shear force diagram. Okay, in the shear force diagram. So complete the diagram, we will draw the shear force diagram, and from the shear force diagram, we get the maximum moment of bending moment diagram, and we can check whether the calculation is correct or not by using the area of shear force diagram. We check whether we get back the moment that we get in the table. Okay, if not, we have to recheck the analysis. Okay, so the diagram must start at 0, close at 0. That is why the last value that you get after calculation, you will get negative opposite with the moment in the diagram, so that when we plus that 2 value, we get back 0 value. So this is the shear force diagram and bending moment diagram for the beam given in the question. Okay, so that's all for series number 1, beam analysis, considering support settlement. Inshallah, we will continue in the next session with another example. Okay, so that's all for this session. Assalamualaikum warahmatullahi wabarakatuh.